All right, hey, welcome to the third of three lectures on linked lists for our data structures class. So, in our previous lectures, we were developing some of the mechanics and some of the high-level view of how linked lists work, this idea of creating structures on the fly at runtime and structures that reference other structures, so linking these nodes together. What I want to do in here is a couple of things. One, I want to look at how we can use the debugger GDB to help us develop and debug our code when we're building structures in memory as our program executes. We know we can put print statements in our code to see where we are in a loop, for example, or whether a condition is true or false. But a lot of the code we write for working with data structures like linked list is going to be relatively short. And the real challenge is not really the code itself, it's how we use the code. So the code for searching a binary tree, for example, may only be 2 or 3 lines of C. But understanding what that code is doing as it executes is going to be the whole challenge in debugging. So I want to start by looking at GDB and how we can use it to examine the memory of our machine as we're building and manipulating some of these data structures. And then I want to dig just a little further into some of the algorithms for linked lists in particular, for deleting from a linked list, adding to a linked list to keep it in order, and searching a linked list. I also want to look at how those things relate to order of complexity. And then I want to finally wrap up by talking about memory leaks and how we can avoid memory leaks in linked lists. So let's start with some GDB. And I'm going to repurpose the code that we were using in the last lecture. So this was an earlier version of the code where we had just a single list called myList. We initialize it, and then we add 3 nodes to it, a 30, a 10, and a 20. And if we recall, our lists contained a sentinel node. So there's a sentinel, which is called myList in our case. And we put a magic number up here just so we would know we were looking at the sentinel node. And then since our code adds a 30 and then a 10 and a 20 and we insert in the beginning of the list, we're going to see that a 20 is right after the sentinel, followed by a 10, followed by a 30. So these things get inserted in reverse order. So here's going to be a node containing a 20 and then a 10 and then a 30. And the next fields are going to point like this. And this last node, the next field, is going to be null, so the special value which says, hey, that's not the address of the next node. It's a flag saying there is no next node. And as a reminder, our node structure looks like this. So this is a node. We've got a data field, which is an int, and we've got a field called next, which has the address of the next node, or our special flag saying there is no next node. So if we compile this and we run it, the print function just prints out our data in order. So 20, 10, 30, that's the order of the nodes. To debug it, we want to compile using the -g switch. And remember, when we say -g, that can go right after GCC. It can go after -o main. It could go after main.c. We usually put it somewhere in the beginning. But remember that -o main has to be sort of one unit, because -o says, hey, I'm going to tell you what to call the output file. And if we say -o-g main, it's going to think we're trying to make a file called -g. So we'll compile it like this. And then to run the debugger, we just say GDB and the name of our program, main. So I'm assuming that you're familiar with GDB. We've gone over this in 224. If you're not familiar, pause here, go back and watch the video from last quarter on GDB, just to refresh your memory on basic commands. But the basic setup of GDB is this tool, this debugger, will let us execute our program either one statement at a time or a set of instructions at a time. But periodically we can have it come back to this prompt where it's asking us for information, for instructions, and we can say, hey, show me the value of this variable, or execute these instructions, and so on and so forth. So we start the whole debug process with the word start, and it always puts a temporary breakpoint right at the beginning. So if we say next, it will go ahead and start executing our code, and it's about to call the init function. Now if I print the value of my list is currently 0. And it's a pointer. If I try to look at what it's pointing to, I'm going to get an error because I can't access memory location 0. So I'm going to say next, which says execute the next instruction. That's line 17. In other words, call init and then come back when you're done and mylist has been set equal to that linked list sentinel node. So I'll say next, and now if I print mylist, it's got a non-zero value. And if I want to see what's at that address, I can just say print star mylist, and I see, hey, it's a structure with two fields. One field called data, which has this number, and a field called next, which has this number stored. So mylist is the address of this sentinel node. It's got a 99999 in the data field, but the next field is null because it's an empty list. All right, now if I say step, it will actually go ahead and go inside the add function in this case and start executing that function one line at a time. And if we thought there was something wrong with the add function, we could do that, but I'm just going to say next. And it will go ahead and make this call to add, execute all the code in there, come back when it's done, and now it's about to execute this. But at this point, it should have added a 30 to my linked list. So our picture at this point should be sentinel node pointing to a node containing 30, and that node will be pointing to null. And we can see that that's the case because if I look at what mylist is pointing to, right, it's a node with a data field of 99999, that's our magic number, and a next field of this. And that should be the address of our node containing a 30. So I can say print mylist arrow next. Remember the arrow notation says this is a pointer. Follow it to the thing it's pointing to, and when you get there, which is a structure, show me the value of this field. So this should just give me this number ending with 92C0. But the debugger knows that's a pointer to a struct node, so if I say print the thing pointed to at that address, in other words, follow the address and show me what's actually stored there, it should understand that the thing it's about to print is a struct node, and it should show me the two fields. In this case, a data value of 30 and a next field of 0. Alright, so just for reference, if I say step or s, I'll actually go inside my add function, and let me do some next now. So it's going to malloc some space. So before I call malloc, temp is, some number. When I execute the malloc function, temp is now a different number. It's 92E0. That's the new location where it's going to create a new node. And if I print star temp, it's got a bunch of zeros in it, but this statement is about to store our data value. So I'll do that, and now if I print star temp, its data value has been set to 10. And then it's going to set the next value to whatever our sentinel node is pointing to. So I can say next and print out star temp, and our temp node has a value of 10 and a next address of 92C0. Well, that's what our 30 was. So let's just step through this and get out of here. And now if I print star mylist next, so mylist is the sentinel node. If I print mylist next, that's our new node that we just created with a 10, which is pointing to 92C0. And if I look at that thing's next field, it's pointing to a node with a 30 and the next field of 0. So I can go ahead and add this 20. So I'll execute that. And now if I print mylist, it's our sentinel node. If I print mylist next, that's the node we just added. It's got a 20 in the data field, and it's pointing to this node, which has a 10 in the data field, and that's pointing to this node, which has a 30 in the data field, which points to next. So there's our linked list. A sentinel node followed by a 20, a 10, and a 30. And that's, what we expected our list to look like, 20, a 10, and a 30, and the 30 is pointing to null. So that's how we can use the debugger to examine our memory as we're stepping through these functions. The other thing I want to mention is that the print statement is really powerful inside GDB. For example, suppose I wanted to add another node containing a 50. Well, I can't just call my function from here, right? I can't just say add mylist 50 because GDB doesn't know about the add function, right? But I can say print, or just a P, and an expression, and GDB will say, okay, well, to print the value of this, I need to make this function call. And so it'll go ahead and call the add function. And, you know, it's a void function, so it returned void. But I didn't really care what the return value was. What I wanted to do was get it to call this function. And now if I print mylist, there's our sentinel, but it's pointing to a node containing 50, which points to a node containing a 20, which points to a 10, which points to a 30. Remember, I've got a print function, so I could say p print mylist, and this will, in order to be able to fulfill my request of printing the value of this expression, it'll have to make this function call. So this is a way that I can trick GDB into calling a function, in this case the function print, which, as we know, goes through our linked list and prints out each data value. So we can work with GDB and get it to do things on our behalf by using this print function. And this also works with you know, putting in breakpoints and stuff. So for example, if I say break print, that'll put a breakpoint right at the beginning of my print function. And now if I say, hey, print the value of print, I can get it to start executing my function, but it's inside the print function and it's about to execute, you know, the beginning of that. So line 55 is where my print statements begin. And now I could, you know, work my way through my code one step at a time and see exactly what it's doing. I can print out temp and see that it's a pointer to a node. I can print it star and I can see that's the first node. And if it was doing something wrong, if it was printing the sentinel or skipping a node, right, I could use this kind of debugging to try to understand where it was and what my code was doing and compare that to what I wanted it to do. And while you're doing this, right, do you want pictures? Do you want to keep making that connection between what you're visually imagining the memory to look like and how you want that to change, and the actual statements of code that cause those changes to occur? Alright, so next thing I want to do is look at a memory map and see if we don't know exactly what these structures look like and so on, we can still just look directly at the memory of the system and get some understanding as to what the data structures look like. And this will be useful as our structures get more complex. So let's take a look at the bare memory just by using some examine commands in GDB. Alright, so one more thing we want to do with the debugger is when you're working with a data structure, so you're building up things at runtime, right? You can't just look at the code and know which variables are where, but you're actually creating the structures on the fly. And you know, we draw pictures like this to help us think about the logical organization of memory. So we have a sentinel node, it points to a 20 and then a 10 and a 30, and that points to null. But sometimes when we're actually trying to debug our code, we need to see what actually has been placed in memory and which things are pointing to what and so on. And this picture kind of, you know, gives us a high-level view of what we want to have happen, but this isn't necessarily reflected by what's actually going on in the memory. So it can be useful to make what we can call a memory map of the memory of the computer, and we can do that pretty easily with GDB. But we need some patience. We need a good clean sheet of paper, nice pencil or whiteboard. And so let's play around with this. Let's go ahead and run the same program we were running a moment ago. So this will build up a linked list. I'll just next my way through the 3 add instructions. And so we execute that last add. We should have something that looks like, you know, a sentinel node pointing to a second node, a third, a fourth, and that one points to null. But let's actually see where things got placed in memory. So I can say, for example, print star mylist, and I can see what's at the location that mylist is pointing to. But if I just print mylist itself, I can see mylist is just a number. It's an address. And most of our addresses are going to be a bunch of 5s followed by 4 digits that are more interesting. So I'm going to write my addresses with just these last 4 digits so I don't have to write a bunch of 5s. And I'm going to record the fact that my list is at location, has a value of 92A0. And so I'm going to start making a picture of what our memory looks like. So at location 92A0, what are we going to find? So I'll put addresses over here on the left, and I'll put contents over here on the right. So we can use the examine command X, and I can say examine this location. And I can see that what's stored there is this number 1869F. Now if I examine /D, I can examine that value in decimal, and hey, there's our 99999. But if I examine it in hex, right, it looks like that. Mostly we're going to work in hex. But I can note in my map here that this is the value 99999. And that's the data value of our Sentinel node. Alright, if I just hit examine again, it will show me what's in the next location, and that looks like a 0. So we've got a 0, and that's at location 92A4. And then if I hit this again, I'll see what's at location 92AH. And that's a bunch of 5s. And if I look at the next location, that's 92AC. That's another bunch of 5s. So here's what my memory map looks like so far. At 92A0, which is the value of my list, I've got my data value, followed by a 0, followed by 2 bytes that look like they go together to form an address. This whole thing is what we call the next field of our structure. And this piece here, this is the most significant byte, and this is the least significant byte. So if we put this and this together, what do we get? 0, 0, 0, 0, 5, 5, 5, 5, 5, 5, 5, 5, 9, 3, 0, 0. And if I say print my list arrow next, that's exactly what we see. 8 5s followed by 9 3 0 0. Well, this address here, 9300, that should be where our next piece of data and pointer are stored. That should be the next node in our linked list, the node immediately after the Sentinel node. This should be our 20 node. So let's go ahead and examine memory. So let's examine what's at this location, and that's 14 hex, which is 20. So I'm going to add this to my map. I'm going to say 9300. And that's got a 20. And then the next location, 9304, that's got a 0. And the next location is 9308, and that's got a 5555 92E0, and that's followed by 4 zeros, 4 5s. So I've added those to our memory map down here, and I put some space between 92AC and 9300. So there's our data value. There's an extra 0 sitting in there. We'll talk about that in a minute. And then there's these 2 bytes that if we put them together, we get a bunch of 5s followed by 92E0. Alright, so let's go ahead and see what's stored at location 92E0. And I'll make some space for these bytes. So let's put in the address 92E0. And so that's the number hex A, which is a 10. So 10 decimal followed by a 0, followed by 5555, 92C0, and then followed by some 5s. All right, so what is this? This is our data value. This is our next value. This is a data value. This is a next value. And now let's look at what's location 92C0. So let's examine 92C0, and that's got a 1E, so that's 16 plus 14, that's decimal value 30, followed by a 0, followed by a 0, followed by a 0. So I just filled in these values. This is data, and this is next. But when the next address is exactly 0, 0, that's null. That's saying, hey, there is no next node. This is the end of the list. So this is your linked list, right? This is how this structure has been stored in memory. And so some things to note. There's some dead space here between 92B0 and 92BF. There's some space here. There's some space here. So I didn't list all of the addresses here. But our list begins here. And these 2 bytes tell us where the first node of the list is. That's at 9300, that's a 20. And the 20 points to 92E0, which is a 10. And the 10 node points to 92C0, which is a 30. And the 30 node points to a 0. So that's Sentinel pointing to 20, to 10, to 30. So that's the list. And as we add more things to the list, as we delete things from the list or move things around, this map may change, right? But our 10 node is always going to be here, but it could be that our 10 node will point somewhere different. For example, if we add something after the 10 before the 30, then this would point to some new location. And so as we're developing our functions to do, searches, inserts, deletes, and so on, if things start going wrong, we can come back to our memory map and we can say, hey, where is this node pointing, what's pointing to that node, and so on. And if we do this carefully at each step, we'll eventually find out where something is happening that's different from what we expected. The other thing I want to point out is that, if we look at our data structure, so let's just look at the very beginning here. We have our node. It contains an integer field and a pointer field. Pointers are going to be 16 bits, so 2 bytes. Integer integer is 1 byte, right? So 32 bits. Pointers are 64 bits, so 2 bytes. So that's our data field. Those 2 things make up our pointer. But there's this extra byte sitting in here that's not being used. There's an extra byte right here. There's an extra byte right here, and so on. And that byte is called padding. It's padding because we really don't like accessing addresses that end with a 4 or with a C. We like addresses that end with a 0 or an 8. That gets deep into the mechanics of how the memory management system works and how memory is physically laid out, and how when you get a card of RAM to put into your computer, how that's organized internally. And it's usually not efficient to access something on a 4 byte boundary. We usually want to access on boundaries of 8 or 16, 32, maybe 64 bytes. So this is what's called alignment, right? And we put padding inside our structures so that each field that we want begins on a nice boundary. So we want our address to begin at something that ends with an 8 or a 0, rather than at this address that begins with a 4 that ends with a 4. That's a deep detail, and when you do computer architecture, you'll learn the details of that. But if these paddings were not here, if we just kind of packed everything in, it would take less memory, right? We'd only need 12 bytes to store the structure instead of 16, but the efficiency would go way down. It could take twice as long to access our information. So, so those are things to be aware of, and even if we don't understand them, we should be able to recognize, that the address does not begin immediately after the data, so that as we're working through our structures in the debugger, we have a clear idea of what is stored where. All right, so let's talk about some other algorithms that we use in manipulating linked lists. All right, so there's other things we'd like to do with linked lists besides add nodes and print out the list. So one thing we might want to do is delete a node. So let's imagine we have our sentinel, and this points to, let's just make a sorted list here. Let's just suppose we have a 10 and a 20 and a 30 and a 40 and a 50. All right, so there's our linked list, and suppose we want to delete the 30 node. So to do this on paper is pretty easy. All we need to do is take this arrow that's coming out of 20 and have it point to 40. And if we do that, the 30 is deleted from our list, right? We'll never reach it. We'll start here, we'll follow to a 10, a 20. When we see what the 20 is pointing to, it'll be the 40. The 40 points to a 50. The 50 says I'm the last node in the list. Where's the 30? 30's been deleted. So the process, the mechanics of deleting the 30 from the list are really simple. Just take this arrow right before it and point right after it, and 30 gets left out. So how could we do this in an algorithm? There's a few different ways to do this. So one way is to march through our list until we get to a node that has the value that we're trying to delete, and then take the node before it and have that point where this node to be deleted is pointing. But going backwards in this list is a little tricky, so we can move forward and keep a pair of pointers, but we can also just choose to look ahead one spot. So we could start off with some temporary equal to our sentinel. So here's temp right here, and we could say well, temp next is not null. So as long as our temporary pointer is pointing to another node, let's see if we should delete that next node. So should we delete temp next? Now we know temp next is not null, so we're safe examining temp next. So I could say something like if temp next data equals 30. So if the next node's data field is 30, then we should say delete temp next. All right, and if not, we're just going to say set temp equal to temp next. All right, so temp starts off at our sentinel node. Temp next is not null because it's pointing to the 10. Is temp next data equal to 30? No. So we're going to say temp equals temp next. Well, if this is where temp next is pointing right here. The effect of that is we change this temporary variable to point to this next node in the list. And then we go back up. Temp next is still not null. Is temp next data equal to 30? Well, temp next is 20. 20 is not equal to 30. So we're not going to do the if statement. We're going to say temp equals temp next, and that moves temp further down. So we are moving through our list one node at a time, And at each point we can use this temporary pointer to interact with that node that we're pointing to now. We're going to do this for all of the algorithms we're going to develop. So at this point, temp is this 20 node. We go back up to the top. Temp next is still not null, so we can say is temp next data equal to 30? Well, temp next is this node, and its data value is 30. So if we're inside this if statement will be true. It means temp is pointing to the node we want to delete. So how do we delete that? Well, we should simply take temp next and set it to whatever that next node is already pointing to. So we set it equal to temp next. So remember, we do these evaluations right to left. First we're going to take temp next, that's this 30 node, and we're going to look at its next field. Well, that's the address of this 40 node. And now we're going to say temp next equals that address of the 40 node. Well, that's what does the magic of taking this and changing it so it points to that. And then we can just say return. That's all there is to it. Sentinel points to 10, points to 20, points to 40, points to 50. Now, if we go all the way through this, if we wanted to delete, say, 55, then temp would come down all the way to here. And when temp got to here, we would say if temp next is not null, well, temp next is null. We kick out of our loop. At that point, we know the thing we're trying to delete was not found. And so here, data not found. So, instead of putting a hardwired 30 in our code, of course, we'd use a variable. But that's the algorithm for deleting from the list. All right. The other thing we want to do is we want to change our add function so that when we add to a list, we can actually add nodes in order. So, if we just say add a 30 and add a 10, and add a 20. Well, the way we were doing this before, we kept inserting nodes in the beginning of the list. So our list would end up looking like this. But it's going to be useful to be able to insert our nodes in, say, increasing order. So that when we start off with adding a 30, our list looks like this. And then when we say add a 10, it looks like this. But then when we say add 20, we actually sandwich this 20 in between the 10 and the 30. So that no matter what order we add our nodes, the list always ends up sorted, say, from smallest to largest. And so we can do the same thing. We can move through our list one node at a time. So let me put our sentinel back here. And let's have a temporary that starts by pointing to our sentinel. And where do we know to insert our 10? Basically, when we find a node that's bigger, sorry, to insert a 20, when we find a node that's bigger than 20, we want to insert right before that. So we could do something like this. Temp equals sentinel, while temp next is not null. So what do we want to do? We want to say if temp next data is bigger than number to insert, so 20 in this case, then that means that temp would be sitting right here. Temp next data is bigger, so we want to insert after temp. So how do we do this? Make a new node with a data value of whatever number we're inserting. New node next equals temp next. So we're going to create a new node. We're going to put the 20 into the data value. We're going to say this new node's next value should be whatever temp's next value is. Temp is pointing to the 30 right now. This statement will take new node and have that point to the 30 also. And then we can say temp next equals new node. And so that changes this to point to our new node. And we're done. Sentinel points to 10, 10 points to 20, 20 points to 30. We can just return. So that's the end of our if statement. But if this number after temp is not bigger than the thing we're trying to insert, move down the list. And go back again. Alright, so let's say we wanted to add a 50, and this is our original list. Let me make a new list here. So let's suppose we have a sentinel, points to 10, points to 30, and we're trying to add a 50. So temp starts off here, and temp next is not null because it's the 10. Temp next data is 10, that's not bigger than a 50. So we're going to move down the list. Temp goes here. Temp next is not null. Temp next data is 30. That's not bigger than 50. So we're going to move down the list. And now when we say is temp next null, yes it is, right? Because this is the last node. So if we come out of the loop, what do we want to do? Insert after temp. In other words, we want to take our new node 50 and put that after what temp is currently pointing to. Well, that's what we're doing right here. So make a new node. We can have the new node next point to temp next, which is null. Have temp next point to the new node, and we're done. And the other edge case, if we wanted to add a 5, for example, we would start with temp pointing to the sentinel. We're trying to add a 5. Temp next is not null. Temp next data is 10. That's bigger than the thing we're trying to insert. So we'll make a new node with a 5. We'll have the new node next equal temp next. Well, that's going to point to the 10. And we'll have temp next point to the new node. Well, temp is the sentinel, so now our sentinel points to the 5. And we've got our sentinel points to 5, points to 10, points to 30. So this little algorithm will work for all cases, inserting in the middle, at the end, or in the very beginning. So that's how we can add into a linked list. And then searching is really kind of the easiest of all. So say we want to search for n. So temp equals sentinel next. And you know, our search, we would have to pass the sentinel and the thing we're looking for. So this is pseudocode, it's not really C. So make a temporary that points to the first data node, and then if temp data equals n, we can return a 1 saying, hey, we found a node containing a value of n. Otherwise, temp equals temp next. And we're going to want to do all of this while temp is not null. If we get all the way through our list, we've taken temp and moved it to the next node, but the next node is null. We're out of nodes. We didn't find our data because we didn't return, so we just return a 0. So searching, pretty straightforward. Alright, last thing I want to talk about is memory leaks, because we're leaking memory all over the place in these algorithms. Every time we allocate a node, every time we create a new node to add, we are calling malloc, and if we don't call free at some point, right, these making of new nodes, that's going to result in memory leaks. And certainly when we delete a node, right, we're trying to delete a node, so we change the previous node to point past the node we're deleting. if we take this 20 and we point it to the 40, this is a classic memory leak, right? There's memory that was allocated for this 30, but, you know, nothing is pointing to it. Once we leave this function, there's no way that we can free that memory. That'll be a permanently lost memory leak. Still cleaned up after the program exits, but is considered a unreachable lost block of memory. So this is a really easy case to deal with, right? Temp next is the thing that we're deleting. So we can say something like, you know, make a struct node, call it save equals temp next. So save will be just a temporary variable that points to the thing that we're deleting. Go ahead and change the pointer so the previous one points past that next one, but then before you return, just free that block whose address we saved. So when we say free save, this gets released from memory, goes back into the free memory pool. It's not a memory leak. But when we build up a linked list and at the end of everything we want to exit our program, all the nodes that we've allocated that we haven't deleted will be memory leaks. They'll be blocks that are allocated when our program exits. So how can we prevent those kinds of leaks? We can perform a cleanup operation at the very end. So here's our sentinel. Let's say it points to a 10, points to a 20, points to a 30, and this is null. Alright, so how do we clean up? Well, there's a nice little process we can use here, sort of a trick. Imagine that you're walking across a river, right, and you want to make yourself a pathway. And so, you know, somebody has put down a series of stepping stones for you, and you're going from this side to the other side, and your goal is that when you get over here, all of those stepping stones should be removed so that there's no path so someone can't follow you, right? And you don't want to get your feet wet, right? You want to use this path to get across, but while you're going across, you want to get rid of those stones, right? So return these to the free memory pool. So you can step on this stone, right? And while you're standing here, you can't get rid of that stone. You can't get rid of the next one because then you won't be able to follow the path. So you really need to move to the second stone, and while you're here, turn back around, pick up that stone, and toss it somewhere. And now take another step to this third node, look back over your shoulder, pick up this stone, toss it away, go to your fourth spot, clean up this one, go to your fifth spot, clean up this one, get back to the shore, clean up this one, there you go. You followed the path, but as you followed it, you cleaned up the things behind you. So we can do exactly that with our linked list. So we can start off with something like temp equals sent. And let's set temp equal to sentinel next. So this is our temp. And let's record previous equals sent. So we seed the whole algorithm by saying here's the previous node, here's our current node. Alright, and we're going to say let's free previous node. So we're going to send that back to the free memory pool. Set previous equal to temp. So this becomes previous. And then temp equals temp next. So here's temp. Right, so we cleared up that block while we were standing here. Temp shows which one we're standing on. Now we move to this block, and we're going to free the previous node. Set previous equal to temp. Set temp equal to temp next. So now we're standing on this last node. Come back to the top of our loop, we're going to free previous. We're going to set previous equal to temp. And we're going to set temp equal to temp next, which is null, so temp equals null. And then if we come back to the top of our loop, we'll free previous, set previous temp, but this is going to segfault if we say temp equals temp next. So let's put this whole thing in a loop while temp is not null. So temp's not null, we'll clear up all of these. When we get to this last block, we freed the previous, the 20, we set previous to the 30, we set temp to null. Come back up here, this is where we're going to kick out of our loop. But after we exit our loop, we're kind of pointing to, you know, the end of the list, the other side of the shore, but this node still needs to be free. So we'll just free previous. So we free that. That releases that. We're done. Return. So that's our cleanup algorithm. Try the edge cases. Suppose our list looks like this. An empty list, a sentinel node that points to null. So temp is going to be initialized to sent next, which is null. And previous is going to be this sentinel node. We'll say, well, temp is not null. Well, temp is null, so we'll exit our while loop immediately. We'll free the previous, which is this node, and return. That's exactly what we wanted it to do. So if we try to clean up a list that has no data nodes in it, this will simply free the sentinel and return. If there are data nodes, this loop will free all of the data nodes except the last one, and then this final free outside the loop will free the last node. So that'll take care of releasing memory, keeping us from having memory leaks. Alright, that's it for the basic algorithms. So you've got lots of opportunity in the practice problems to write code to explore these ideas. And just keep in mind edge cases. There's a lot of ways to do this. The algorithms that I'm describing for you will keep the edge cases clean. They should not fail on the cases where a list is empty, where you're trying to delete the last node of a list or things like that. But think about them as you're working through the algorithms, writing up code. Even if your code works, right, you should have confidence before the first time you run it that it's going to do the right thing. So work through the pictures on paper, pretend you're a computer, you know, update the values of variables and what things are pointing to, and so on, and convince yourself that these algorithms will work. And then, you know, actually try the code and verify they do the right thing. All right, have fun. Thanks.